Okay, Roberto, maybe now we can start. So welcome back to everybody to this last day of the first week of the school. So the first lecture today will be by Roberto, concluding the course on EFT. So please, Roberto.
Okay, so thank you. So as we said yesterday, today we are going to discuss, I hope quickly, which means maybe 1 hour or maybe less, the case in which you construct an effective field theory without knowing the UV dynamics. Okay. In fact, effective field theories are useful even more in this case. Okay, despite the fact that you don't know the UV theory. So the first question, of course, is well, okay, but how can you make predictions given the fact that the effective coefficients are not known because you cannot match to a UV dynamics? Well, okay, there are at least 3 possible ways to go. So, how to compute, or if you want to have quantitative predictions if UV theory is unknown. The first possibility is to focus on observables, or at least on contributions to observables which are calculable within the effective field theory. Calculable means that these quantities do not depend on the effective coefficients. How can this be possible? Well, because the effective operators, as we explained, give contributions to observables which are polynomials which have a polynomial dependence on the momentum. And that's because, exactly because the operators are local operators. Okay? The fact that they are local means that they depend on powers of derivatives and fields, of course. And these local dependence in momentum in position space, once you Fourier transform in momentum space, gives you an analytic dependence on momentum, in particular polynomial dependence on momentum. So everything which is not non-polynomial, as we said, also we saw it in the matching, must come from the exchange of light degrees of freedom, not heavy ones. Okay, so you can use or focus on calculable quantities, which are quantities which are non-analytic actually both in momentum and in the parameters of the effective field theory. Parameters which appear in the Lagrangian the effective field theory, which again should not be the coefficients, of course, which are unknown, but all the others, okay, are parameters which appear, masses and couplings which are in the renormalizable part. I mean, those which are known. So non-analytic in momentum and in effective parameter are, okay, quantities which are calculable. They do not depend on the UV theory, on the UV dynamics. Examples of calculable observables. Well, the first, there are a few, so I just mentioned maybe two or three examples, but there are several situations in which you can identify calculable quantities. So the first example could be long-range potentials among light sources. Okay, sources made test particles. Okay, currents, whatever, made of light particles, and the potential that these currents or particles feel between each other is a quantity which is calculable. Why calculable? Well, because again, if you think in terms of in position space, okay, you are testing an effect at a finite distance. Okay, while these operators, each of these operators gives a contribution which is local, which means that as by definition of heavy modes, acts on short distances. Okay, which in position space you can parameterize in terms of delta functions or derivative of delta functions. Okay, so long-range potentials are calculable. And one example is corrections to the Newtonian potential coming in an effective field theory of quantum gravity. So if you take GR and you quantize it, okay, as an effective field theory, which means that the Einstein action term is the first in an expansion in derivatives and fields, then okay, this will allow you to make predictions which are well, some of these quantities that you can compute will depend on the effective coefficients of, for example, higher dimension terms which have more derivatives, for example, Ricci square, okay, derivatives acting on Ricci, and so on. But others, like for example the correction to the Newtonian potential, which is an effect occurring on a finite distance, those will be calculable. Okay, of course, this correction will be super small because it's suppressed by M Planck, but still it's an ambiguously calculable quantity that you can consider computing within the effective field theory. So you don't need to know the full quantum gravity theory, okay, which eventually at very low energies, at energies at which you do the experiment, will reflect into some higher dimensional operators with unknown coefficients. You don't need to know whatever string theory completes quantum gravity seen as a quantum field theory. You just need, okay, you just need to know the properties of the low energy dynamics, okay, which are well defined. So corrections to the Newtonian potential in GR as an effective field theory. And here I can point to you to the paper of Donoghue. So Donoghue made very nice results where he computed this effect. So look at this paper. Then the other possibility and the other concrete example of range potentials is the Casimir potentials. And here I would add, for those of you who know a little bit of extra dimensions, including the Casimir effect in extra dimensional field theories. So if you have a field theory which lives in extra compact extra dimensions, spatial dimensions, like for example a circle, okay, so there is a Minkowski 4 times a circle with a given radius, then the fact that the x dimension is compact leads to a potential coming from fluctuations of the vacuum. And these potential scales like 1 over the radius to the 4th. Okay, so this is an example in which there is a non-analytic dependence on a parameter which appears in the effective field theory action, which is in this example is 5-dimensional, which in this case is the radius. Okay, so including Casimir energy or potential in compact extra dimensions. Okay. Now another example of calculable quantities is, for example, the logarithmic evolution of gauge couplings. That's how somehow we can get an insight on a possible grand unification theory, because we are in an effective field theory, which is just the standard model seen as a low energy description of some more UV complete theory, and we run the couplings, and this running is not affected by whatever new physics you have at the gut scale, at the heavy scale. Of course, eventually there will be corrections at a very high scale, but the running itself is something that you can compute. You can compute because it's non-analytic in momentum. It's just a logarithmic evolution of your couplings. Okay, so logarithmic evolution of dimensionless, or if you want, of any coupling. And then, okay, and then whatever non-analytic dependence of, for example, of scattering amplitudes. Okay, so if you compute the scattering amplitude, for example, there are beautiful papers by Weinberg on pi-pi scattering, and then he explains, even in his book, that there are terms which in the pi-pi scattering amplitude, which you compute in the chiral effective field theory, which these effects, which are nonlinear in the momentum, in the Mandelstam variables, are free from ambiguities due to the UV theory. Okay, so you don't need to extract the chiral coefficients in order to compute these coefficients, these effects. So non-analytic dependence of scattering amplitudes. So this non-analytic dependence entirely comes from light degrees of freedom, and in fact, including the imaginary part of scattering amplitudes, which of course you know comes from the possibility of exchanging on-shell intermediate states, which have to be light states. Okay, so these are just 3 examples where you can compute things even in an effective field theory whose UV completion is unknown. The other possibility is to fit the effective coefficients from experiment. So you have a certain parameterization, okay, in terms of effective operators, and you decide that you can truncate at a certain level in the energy expansion because you have a certain precision, you aim at a certain precision, and then at this point you have an effective field theory with a finite number, a given number of effective coefficients, which you can extract from a corresponding number of experimental inputs. Okay, so extract effective coefficients from experiment. Okay, and the example here is the one of chiral effective field theory, chiral perturbation theory.
Okay. Roberto, we have a question.
Please.
When we compute the imaginary part of scattering amplitudes, what does forbid us to reconstruct the complete scattering amplitude using dispersion relations?
Yes, that's a good question. You can, but eventually you will see that there will be terms so you can integrate, you can write a dispersive relation, dispersive integral, which is an integral over energies, okay, and the integrand involves the imaginary part. But this, in general, does not reconstruct the full result. So you cannot reconstruct entirely the real part of your scattering amplitude, because there are terms which eventually correspond exactly to local contributions coming from the local operators, which you have to add by hand, okay? And for example, normally the need for having such terms appears because the dispersive integral is divergent. Okay, if you write a vanilla formula, a plain formula without worrying too much, then eventually you see that in general it diverges. Okay, the integral of energies diverges. So you need to make subtractions, and subtraction means that you have to write the dispersive integral for a more converging integrand, okay? But at the cost of introducing, of losing, if you want, predictivity, because at this point, making subtractions implies that your result will include not only the dispersive integral, but also other local terms, which are a polynomial, if you want, in the external momentum. And the coefficients of these polynomials are exactly the effective coefficients that you don't know. Okay. In fact, taking the imaginary part of this formula, you are left only with the dispersive part, because all the polynomials don't give you an imaginary part. Okay. So this is, let's see where, well, it's explained in, there are several references. Maybe I can give you on Slack, on the Slack channel, I can try and find some references. There is a comment on Weinberg, which is, however, very, very short when it discusses the dispersion relation, but it's too short. Okay, so I'll give you maybe some reference. I will find it. Okay. I hope it was more or less addressing your question. Okay. So one way to make quantitative predictions is to extract the unknown coefficients from the experiment. This is exactly what is done in chiral effective field theory. The final possibility is to estimate the effective coefficients. And now this requires a power counting, a set of rules which allow you to make an educated guess about the size of these coefficients. Of course, this is not a way to compute. Okay, the only way to compute in a precise way it's 1 and 2, but still, okay, it's very useful. Many situations it's very useful to have an estimate of the size of the UV physics. Okay. So even though you cannot make a precise calculation, having an estimate is very important in many situations. Okay, but this requires a set of rules which goes under the name of power counting, which allows you to estimate under some assumptions, which now we are going to discuss, the size of the effective coefficients in terms of the parameters of the UV theory. Okay, so this goes under the name of power counting. So let's try, let's make an explicit example, and this will illustrate the art, if you want, of estimating effective coefficients. This is not an exact science, but it's rather an art, because as I'm going to stress several times during these lectures, during this final lecture, estimating these coefficients requires making some assumption on the UV dynamics. So you cannot estimate coefficients blindly, okay, in a completely model independent way without making any assumption on the UV theory. That's impossible because different UV completions will give you a completely different size of the effective coefficients. Okay, so if you change the UV, then of course you can change vastly the values of the effective coefficient. So you have to make some assumption and put yourself in a class. Assume that the UV dynamics is of a given kind. For example, is it strongly coupled? Is it weakly coupled? If it is weakly coupled, it is minimally coupled or not. So there are several layers of assumptions that you can make to get to a formula which gives you an estimate. Deciding which assumptions you want to make, of course, leads you to a different result. So that where to go, if you want, is a bit arbitrary and requires a bit of ingenuity. Okay. So first of all, how can we write very simple estimate of the coefficients? Well, we need to take into account their dimensionality. Okay, so if they multiply an operator dimension d, they will have dimensionality 4 minus d in mass, okay, in energy. But that's not enough because typically, and actually always, these coefficients imply a certain number of powers of couplings of the UV theory. So you have to take into account how many couplings there are, how many powers of the couplings there are, and how many powers of the UV scale enter. Now, of course, you see, we are already forced to make an assumption because which scales, which energies, which masses of the UV theory will appear in the coefficients, and how many of these scales there are, and how many couplings there are. Think of the standard model. If you go to low energy, for example, you integrate out the weak, the heavy states interacting weakly, well below the electroweak scale, then you can write an effective theory, which might be one charge under SU3 color cross U1 electromagnetism. But then how many scales do you have? Well, there are several scales. There is the mass of the top, the mass of the W, the mass of the Z. There are several physical scales which characterize the full theory. So and several couplings. So you had to make some assumption. The simplest possible characterization of the UV theory, which may be oversimplified, but it's a starting point, is one in which you assume that there is only one scale characterizing the whole spectrum of particles in the UV theory, and one coupling strength. Okay, so this is I think is probably the simplest power counting. One scale, one coupling, one scale which I will denote M star, and one coupling which I will denote G star. Okay, so the coefficient CI, okay, will scale like, well, this CI will have a certain dimensionality, so it will scale like a mass, which I call M star, to the power D minus 4, so DI minus 4, where DI is the dimensionality of the corresponding operator. Okay, and then in the numerator there will be, in general, how many couplings? Well, there will be a power which is equal to, this is Ni minus 2, where Ni is the number of fields in the operator OI. Because you know, if you have a cubic interaction, so this comes as an operator, as a local operator involving three fields. And this goes like a coupling, right? So a quartic interaction goes like a coupling square, and so on. So the general rule is that you have coupling to the number of fields minus 2. Then, however, these effective coefficients might arise not simply at 3 level, but they could arise at a certain order in perturbation theory in the loop expansion. So in general, there will be another factor, G star square, again, where there is only coupling, divided by 16 pi squared to the L, where L is the number, is the loop level, okay? Number of loops required. Okay, so that's the naive estimate that one can make. Of course, things might be modified by selection rules. So, for example, if there are operators which are generated only involving some couplings which are, for example, those of the standard model, the standard model, the effective field theory, okay, because there is a violation of, there is a need of violating or breaking some invariance, which is only broken by the couplings of the effective field theory, as we are going to show in the example that I want to mention. Then instead of G star here, there might be other couplings of the low energy theory. So not couplings characterized in the UV, but couplings appearing in the low energy effective field theory, which might be even smaller, okay, or even larger, okay. So at this point, maybe this loop suppression is not a loop with G star, but it's a loop with G of the effective field theory. In any case, this is the starting point, okay, to make an estimate. So let's consider a concrete example.
Roberto, before the example, we have a couple of questions.
Please.
Yeah, my question is, if the UV theory, we suppose it is renormalizable, don't we get a renormalization scale, and so the possibility of having, for example, non-analytic contribution in this CI? For example, the logarithm of mu divided by m star square.
This non-analytic dependence, as we saw in the matching calculation, can only enter in the effective coefficients necessarily. It cannot happen. It cannot appear. All the dependence on the UV parameters is encoded in the effective coefficients. It cannot appear in the low energy theory itself.
Okay, and so why we do not have the possibility of having such functions in these CIs?
No, the CI, yes, no, of course. The CI the value of the coefficients is unknown. Okay, so take this coefficient to have any value. Okay, it's unknown. So I'm saying that you're talking about number 2, right? So, sorry, number 1. So number 1 is right. So you're talking about when you can when a quantity is calculable. It's calculable when it's non-analytic in the parameters of the low energy theory, which are the momentum itself and all the coefficients of the coefficients which appear in the action, not necessarily in the Lagrange, but in the action of the low energy theory. Anything else must be encoded in the effective coefficients, which are unknown. So of course, these coefficients, if you know the theory, will depend in a non-analytic way on the parameters of the UV theory, but we don't know them. Okay. So maybe you are asking here.
Yeah, exactly.
Sorry. Now I understand. While here you cannot have. Well, First of yes. So there will be corrections which are non-analytic, of course. That's a good point. Sorry, now I understand. For example, a log dependence on M star. But here, of course, on dimensional ground, this will be present, okay? But it will not change the size of this coefficient. Okay.
Okay. So we can multiply by a function of a dimensional parameter,
yes.
but we do not know this function.
Exactly. So you see, this is an estimate. So don't pretend too much. It's not a calculation. Okay. By no means. It's just a very, 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 very naive estimate, which just keeps into account the dimensionality in energy, the dimensionality in couplings, and how many loops you need to create this effect. Then, of course, here there is an order one coefficient, which might be a function of non-analytic function of all the parameters, absolutely. But this unknown function, I assume that it's of order one.
Okay. Thank you.
There was another question.
Hi, yeah, thanks. This is a bit of a naive question, but does number of loops required just mean the number of loops required to make good predictions?
Sorry, say it again.
Oh, sorry. Does the number of loops required just mean number of loops required to make reasonable predictions?
In number two, how many?
In number three, on the very bottom of the board, L is the number of loops required.
So here, so this is the number of loops required to generate the effect. For example, if you have heavy modes, okay, and you integrate them out, you will generate these coefficients. But at which level? Because, for example, in the Fermi theory, you integrate out the W and you get a four fermion operator at 3 level. Okay, so then the estimate will be C Fermi, okay, and this is psi gamma mu psi squared. Let's call it C Fermi, okay. C Fermi goes like a coupling squared, right, which is G and G, divided by M star, which now will be the mass of the W squared. So this works well because it's generated at 3 level. But in our example of matching, the operator phi d phi squared was not generated at 3 level. It was generated at 1 loop. So the estimate, let's call this C, the estimate was not y squared divided by m fermion squared. There was another y squared divided by 16 pi squared. You see? So that was also it was also an example captured by this simple power counting, because there was only one coupling and one scale. Okay, but L there was 1. Okay.
Got it. That makes sense. Yeah, thank you.
Sure. Okay, so now, however, I want to make another example. Okay, if you want, take as an example these two, but I want to make an example in which you really use other tricks. Okay, so in which the estimate is slightly less simple. Okay. And in fact, I think it's an instructive example. I mean, a real one. So consider QED as an effective field theory, and why will you think you would think that you have to consider QED as an effective field theory? Because it is. Okay, so QED is necessary in effective field theory. It's an effective field theory because, as you know, the coupling runs, okay, and the gauge coupling runs, and the beta function is positive. So eventually you have a Landau pole. Of course, the scale at which you are forced to replace the theory with something else is very, very high. But at least you know that QED cannot be the full theory. Okay, so QED cannot be seen as a full theory, contrary, for example, to QCD, because QCD is asymptotically free and it can be extrapolated to arbitrarily high energies. So QED must be an effective field theory. At this point, you might be worried about the contribution coming from higher order operators, which might destroy the low energy predictions, starting from the very first one done by the one on G minus 2, which is corresponding to an operator, which is a dipole operator of this form, psi. So this will be, well, okay, times f mu nu, where f mu nu is the field strength of the photon, okay, and psi, for example, is the field describing the electron, or whatever any other light fermi you want to include in your QED theory. For example, they could be also be the muon. Okay, so this will give a contribution to the G minus 2. So it will give a correction to G minus 2. Remember that the magnetic moment of, for example, let's say the electron, okay, or any fundamental particle is given by its spin, okay. Then there is a charge divided by 2 times the mass times G, which is the gyromagnetic ratio, and this G, of course, is 2 plus orders within the effective field theory is 2 plus orders the electromagnetic coupling divided by pi, which means 10 to the minus 3. And then I would add plus, okay, the effects from this operator, okay, plus contribution from O. So this operator has dimension 5, okay, and now you can conveniently define A to be G minus 2 divided by 2, okay. So the contribution from O is one in which delta A is, let me read, because delta A is 4m, let's say delta AE, okay, is 4me divided by E times C of this operator, okay. Let me call it CO. So since eventually the prediction of QED is reproduced by, it matches the experimental value that you extract from data to an extremely good precision, and you don't see particular deviations from this theoretical prediction, at least in the G-2 of the electron, then you can put constraints on this coefficient. So it must be that the scale at which QED is replaced by a complete UV theory has to be sufficiently large in such a way that this coefficient is sufficiently small, okay? So without making any estimate, you can use data and put a constraint on CO. Now, the prediction, the experimental measurement of, for example, of A is, well, it's at the level of 10 to the minus 3, as we said, and has an accuracy of, a relative accuracy of 10 to the minus 9. Okay, so the experimental measurement, and agrees with the QED theoretical prediction up to terms of order 10 to the minus 10, roughly. Okay, so from AE experimental, you get a bound on CO using the fact that there is an agreement between theory and experiment up to terms of order 10 to the minus 10, which, okay, goes like this: 0.25 times 10 to the minus 7 E divided by GV. Okay. So this is something, extracting the bound on the coefficient doesn't require any guess, okay, any esoteric assumption. Okay, so this is straightforward. However, the point is the following: now that you derive this bound, how do you interpret it? Okay, so what does it mean? If you are very sloppy, then you say, but look, CO goes like 1 over m star. Okay, I don't even put coefficients in couplings in actually people usually call it lambda. Okay, if you say, look, I mean, CO is equal to 1 over lambda, and then what does this mean? That this lambda has to be bigger than 10 to the 7 GeV. Okay, if you make this kind of argument, then you are on a wrong track. Okay, because the bound is not as strong as this, because this estimate is not accurate enough. First of all, because it doesn't take into account that this coefficient will necessarily imply some powers of the couplings, and then there is actually some more way to refine the estimate, which shows you that if the UV theory is of a certain kind, then actually the bound is much smaller, much weaker. So how can you argue? But first of all, okay, one thing that you can assume is that the UV theory is weakly coupled. Okay, so let's make this assumption as a working hypothesis. So if the UV theory is weakly coupled, then you may notice that effects coupling the field strength to the electron will not arise if at 3 level, if the UV dynamics is not only weakly coupled but also minimally coupled. Okay, so in other words, if your fields in the UV couple only through covariant derivatives and not directly with a field strength, which again will be necessarily a normalizable interaction, then, and the theory is weakly coupled in the UV, then when you match it to the effective field theory, which in our case is QED, necessarily you will need at least one loop to generate the operator O. Okay. So let's list all the assumptions that we need to make in order to get to the estimate that I want to show you. So UV theory is weakly coupled and minimally coupled. So this means that L has to be at least 1, cannot be 0 over there. Okay, so I need at least one loop. Okay, so this means that my estimate is not simply CO to which power. Well, you see there are 3 fields. Okay, so I could guess that CO goes like some coupling, which I don't know, divided by some scale, which I don't know, times G star squared divided by 16 pi squared to the power 1. So you see that this estimate is already looking differently from the very, very super naive way of writing things, CO equal to 1 over lambda. This lambda is not a physical scale. The physical scale actually is m star, and in the numerator there is a coupling. Coupling which might be small. Okay, and if this coupling is small, this loop factor will also be small. Okay, and you see that the coupling, the coefficient at this point will be much more suppressed. So the physical scale at which new particles will appear is not 10 to the 7 GeV, but it might be very much smaller. However, there is another observation that you can make, which is the following. This operator violates a chiral symmetry invariance of QED. So what is this chiral invariance? Well, you can formulate it as a parity, okay, like this. Okay, so a transformation, if you want, let's make it explicit that it's a parity. Okay, if you want, you can define it this way. It's a chiral parity, and QED is invariant under this operation. Let's call it P axial. Okay, unless except for its mass term. So the mass term, okay, breaks goes to minus psi bar psi. Okay, so this is the only violation, of PA in QED. Okay, in the Lagrangian of QED. So at this point, you notice that our operator violates this invariance as well. Okay, so this suggests that there is another possible assumption that you can make, which is reasonable. You can assume that the UV dynamics does not break this parity, introducing more sources of breaking, if you want. Okay, so in other words, the only source of breaking, both in QED and in QED plus this operator, or if you want, QED is seen as an effective field theory or of a more complete theory, the only source of breaking of PA is the one that generates the mass term. That's a possible, it's a possibility, it's a possible thing that can occur. And if this is the case, then it's clear that the coefficient CO will have to be related to the mass of the electron. Because in the limit in which the mass of the electron goes to 0, also the coefficient CO will have to go to 0. In particular, the operator will also be odd, okay, under the symmetry. Because you see, well, it has exactly the same structure, apart from the sigma mu nu, it has the same structure as the mass term. Okay. In fact, if you write it in terms of chiral fields, then the mass term involves a left and a right field, and that also involves a left and a right field. While the kinetic term, for example, involves 2 left-handed fields or 2 right-handed fields. Okay, so you can formulate the same argument in terms of a U1 axial, okay, where psi transforms as a e to the I alpha gamma 5. Okay, and this leads it's a continuous symmetry instead of a parity, but it gives you exactly the same conclusion. Okay, so how to take into account at this point that there might be an additional suppression due to the fact that the two effects can be related? Well, the trick to take into account this correlation, it goes under the name of a Spurionic argument. So in other words, you can consider the coefficient of this operator, which is a mass term, the mass coefficient. You can consider not as a coefficient, but as a field. In other words, you can assign a transformation rule to this coefficient in such a way that the product coefficient, which now will be referred to as a Spurion, okay, Spurion times operator, is invariant under the symmetry. So under PA, okay, the mass of the electron goes to minus the mass of the electron. If I assign this transformation rule, then you see that the mass term is also formally invariant under the symmetry. And under U1A, instead, of course, ME will transform as e to the minus 2I alpha ME. Okay. So if you do this, then you formally restore invariance of the QED Lagrangian under these symmetries. And then at this point, the operator, okay, the operator O, since it transforms, as well. Okay, so here psi bar psi transforms as e to the 2I alpha psi bar psi, and O transforms in the same way to I alpha psi bar psi. Okay, then it means that the coefficient of O will, the coefficient of this operator O will also transform in the same way. Okay, so the coefficient will also transform as CO going to minus CO, which actually I already wrote it somewhere, and CO will also go to e to the minus 2I alpha CO. Okay, so this means that the coefficient CO, if the mass of the electron is the only spurion, is the only source of breaking, then CO will have to be proportional to ME necessarily. Okay, because the only way to get the right transformation rule, okay, is to use powers of ME. Okay, and the right power here is 1. Okay, so that's the assumption, that there is only one spurion in the theory, in the effective theory plus the UV dynamics, which breaks the symmetry under consideration. And all the other quantities which violate, which are transforming non-trivially under the symmetry, had to be built with this, using this spurion. Okay, and here we get this information that C has to be proportional to ME. So at this point, okay, if we do this assumption, assume that ME is the only spurion of chiral symmetry breaking. Of course, this is an assumption on the UV, okay? Then this implies that CO goes, has to be proportional to ME, okay? And now you see, since it has to have dimension -1, then it will go like 1 over m star square times g star square divided by 16 pi square. Okay, that's a more refined estimate, which is the one that I wanted to get. Okay. Now, if you use this estimate with g star of order 1, this implies now. Of course, at this point, you see that if C is proportional to the mass of the lepton, whose G is -2 you're considering, then it's clear that considering the muon would be better, because you go from half MeV to 100 MeV. So using G -2 of the muon, okay, then it will give you a bound on M star, which is around 240 GeV. Okay. For G star of order 1. Okay, and using G -2 of the muon. So you see that making this estimate, of course, forces you to make assumptions. But if these assumptions are true, then the structure here is completely different, and it even tells you that the right observable to consider is not the one which will give you the strongest bound, is not the G -2 of the electron, but is the G -2 of the muon. Okay, and then you see that the value that you get is way below 10 to the 7 GeV. Now, it turns out that the QED is the effective field theory limit of the electroweak theory. So you know that it's QED emerges from electroweak symmetry breaking from the standard model. So you know that there is new physics entering into at one loop, giving you a correction to the G -2. These are exactly, these particles that you integrate out are exactly the electroweak particles. So so the W, the Z, okay, and you can make a calculation, and you can check whether this estimate is correct or not. Now, question is, are the assumptions that we made fulfilled in the electroweak theory? And the answer is yes, because the electroweak theory, which means the standard model, okay, is weakly coupled. Okay, it is minimally coupled, so necessarily the effect is arising at one loop. And then indeed there is only one spurion, at least if you look at one kind of lepton, there is one spurion, which is the Yukawa coupling, which is the only source of breaking of this axial symmetry. Okay, the only breaking is coming from there because the axial symmetry is one under which different chiralities transform in different ways. Okay, and you know that the only term in the standard model Lagrangian where you can mix different multiplets, which means, for example, the electron left and the electron right, is the Yukawa term. So there is only one parameter which will enter, okay, both in to generate the mass and also to generate this coefficient. Let me do it here. So there are certain type of diagrams. For example, you can have loop of W's, okay, with a virtual exchange of a neutrino. Okay, so this is the lepton, if you want, lepton. Then there is a diagram involving the Z. This is the lepton, and this is also a lepton. Okay, and then the last diagram is the one with the Higgs, which, however, so this is the photon. The one with the Higgs is smaller because of the small Yukawa coupling. So this is the Higgs boson, okay, and here you have the lepton. So if you make the calculation, and the calculation has been done in this paper here, Bardeen et al. Bardeen et al. Nuclear Physics B 46, 1972, page 319. Then you get exactly from this calculation. Okay, if you look at the paper, of course, you will find the complete result. But the complete result scales exactly in that way. It scales like ME, well, actually M lepton, okay, times, now the coupling is the electroweak coupling, which is not of course is a coupling characterizing the UV. It's not the electromagnetic coupling, which is a coupling appearing in the QED effective Lagrangian, but it's a coupling characterizing the UV. So it's G divided by MW squared times G squared divided by 16 pi squared. So that's the estimate that you get. Well, actually, sorry, here there is E, okay? So the G, which I was mentioning, of course, appears here in the loop, but then there is a vertex, which is the usual electromagnetic coupling, okay? So the estimate is pretty accurate, okay, and tells you that the bound on MW coming from these measurements of G minus 2 of the electron, G minus 2 of the muon. Well, in one case, okay, if you use the let's see, exactly, I didn't tell you a number, okay, so if you use the G minus 2 of the electron, G minus 2 of the electron, then you get that M star has to be bigger than 10 GeV. Okay, if you do this exercise, then you get something like 10 GeV with the electron. Okay, this is G minus 2 of the electron. If you do G minus 2 of the muon, then you get 240 GeV. So the conclusion, since you know that the mass of the W is 80 GeV, then it's clear that the experimental precision in G-2 of the electron is not enough to be sensitive to these electroweak effects. But on the other hand, the contribution from the electroweak loops is important, okay, to get a precise enough prediction for the G-2 of the muon. Okay, so you see that these effects are important for the G-2 of the muon. Okay. So you see that making the estimate for the effective coefficients uses a certain list of tools. Okay, you need to know, you have to be able to make assumptions on the UV theory, whether it's minimally coupled, for example, is one of the assumptions which you can do. And then you can use spurionic arguments in order to constrain the form of your result, of your coefficients. Okay, so Spurion arguments are very important. They tell you exactly how many powers of the couplings can appear. Any question on this? I think it's a good, yeah, I see one question.
Yeah, I have maybe it's a trivial question. How can we see the operator we defined? So psi bar, sigma, mu, nu, psi times the field strength involves a 3-point, I mean, 2 spinor fields and just 1 vector field. I don't know, with the field strength, I would maybe ingenuously say that it would involve 2 vectors.
No, but this F mu nu is the photon, eh? Okay, so this is simply d mu a nu minus d nu a mu.
Ah, okay.
Okay, it's not, it's a billion. It's just the photon. There is no non-abelian part.
Okay, thank you.
If you construct the same operator with the non-abelian gauge field, like for example the W and the hypercharge, no, sorry, the hypercharge, no, the W and the gluons, then yes, you also have a quartic term. But here there is only one.
Okay, thank you.
Other questions? Well, okay, before switching argument, I want to tell you one last comment. I want to make one last comment. And the comment has to do with the validity of the effective field theory description. The validity of the effective field theory description is important whenever you don't know the UV theory, right? So the question is, when am I allowed to use my effective field theory to make predictions and on observables, and when instead my effective description breaks down? Well, we know that the effective description breaks down when we do scatterings, when we compute quantities which involve energies of order m star, okay, of order the UV scale. However, m star now is not known. The UV theory is unknown. And in fact, if you measure these coefficients, for example, in the G-2 of the muon, no, you might get to the sensitivity to constrain the coefficients. However, these coefficients are not simply functions of the UV scale. They also involve couplings. They involve more than one parameter, more than the scale. And you see that in order to get a bound on the UV scale, we had to do a guess on the coupling, which, by the way, it's exactly fulfilled. No? It's exactly okay in the case of the standard model as a UV completion of QED, because the coupling is more or less a half. Okay, the G coupling over there. But if the coupling was 10 to the minus 4, okay, then the bound would have been much milder. Instead, if the coupling is much stronger, then the bound again becomes stronger. So this means that the energy at which you expect the production of new particles, scale m star, cannot be inferred from the low energy theory without making assumptions on the UV dynamics. And now you understand that since this scale is the scale at which the effective theory breaks down, this means that the validity, the ultimate energy or validity of the effective field theory cannot be determined unambiguously, but you need to make assumptions on the UV. Let me make another example, okay, which shows you the same things, but it's even more familiar, okay? And it's an historical one. Let's consider again the Fermi theory. And the example is the Fermi theory. Okay, so the Fermi theory is one in which you have, in the effective field theory, you have a coefficient, okay, which you can call C Fermi, okay, and then you have gamma. Let's write actually down. Let's say that this coefficient is measured through. So CF is equal to. Actually, let's put names. So this is minus G Fermi divided by square root of 2, okay? And G Fermi divided by square root of 2 is G squared divided by 8 MW squared, okay? Let's do things a bit more carefully. Times, and let's measure it, okay, through the muon decay. Through muon decay. So muon decay allows you to extract, okay, the coefficient. And so the Lagrangian here is one involving two currents, one of the electron and one of the muon. So you need to destroy, so there will be 1 minus gamma 5 mu, okay, times 1 minus gamma 5 E. Now the same Lagrangian, and this, what does it give you? It gives you the value of this ratio. Again, does not give you the value of MW. It gives you the value of the ratio of a coupling square divided by a mass scale square. So if you use this Lagrangian, the same Lagrangian, in order to make a possibly high energy scattering, so you can scatter, so use LEFT to make scattering of neutrino, muonic neutrino on an electron, which gives you a muon and neutrino electron. So this is exactly what has been done in the experiment which discovered the neutral currents, okay? Because there is also the possibility, if you integrate out the Z, to have a process where you exchange the Z, which is a neutral current process, and where you don't produce a muon, okay? You have again a neutrino muonic. So, and this is the Gargamel experiment at CERN I think in 1973. Okay, so it's a real process, okay, which has been measured, and in fact it was a sort of it was a sort of background to the neutral current signature. Now, if you use this Lagrangian, effective Lagrangian, to make this scattering, now the energy, the initial energy, is not the one of the muon mass, but it can be large. Okay, it can be large, and now you may ask yourself, well, if I increase this energy, will I reach a scale at which the validity of the effective field theory will break down? It's possible, because I don't know MW. And now, if you don't do any other experiment, if you don't have any other information than the mu decay, the cutoff scale, which is MW, okay, can be all the way from the mass of the muon, where you did make an experiment and you did test the validity of the effective field theory, because everything is reproduced by the Fermi-Lagrangian, up to what? Well, up to a place, okay, where the coupling is maximally large. No? You see, if you increase the coupling, then for a fixed value of G Fermi, the mass of the W has to be larger and larger. Okay, the largest possible value is when the coupling is over the 4 pi. Okay, so and this is where if you call this 1 over b squared, okay, then it's the value MW where you have you lose perturbativity and you get a maximally strong value of the physical scale is 4 pi times b. Okay, which you know is of a few TeV. Okay, so that's the range, and the mass, the actual value, the mass of the W, is in between. Okay, so for example, the scale would be very close to the mass of the muon if the coupling was over the 10 to the minus 3. Okay, while for a coupling of order 1, okay, or maybe half, then you get close to 80 GeV, which is the physical mass. And if the coupling is of order 4 pi, okay, then you reach 4 pi V. Beyond that, I would say that is not physically possible. So that's the range of masses that you could expect. But if you only have the experimental information done at the muon mass coming from muon decay, you really don't know where is the cutoff scale. Okay, so the answer to your question cannot be given unless you make an assumption on the value of coupling. So there must be some assumption on the UV dynamics that you have to make in order to answer this question. When is my effective field theory breaking down? Okay, so that's very important because sometimes experimentalists or even theorists try to answer this question without pretending that they give this answer independently of the UV physics, but that's not possible. And this example, if you want, makes it, I think, makes it clear. Okay, but again, also here it was the same story. Okay. Questions on this? Okay, so I think I'm left with maybe 15 minutes. So at this point, I want to discuss about, I'm sorry, I have twice as much material and... a
moment, Roberto, we have a question.
Okay, please.
Hi, is it always the case that it will come as like coupling over mass? Like, is it always the case? Because in the first example that we saw, it did look like the case that you get G square over M square. But like, I'm asking, is it a like given phenomena that it will always be the same power of coupling and the mass?
No. The power is the one that I wrote over there. No, it's the number of legs. Sorry, the number of fields minus 2. Okay, so in this case, it's a 4 fermion operator. So there are 4 fields, 1, 2, 3, and 4. So the power is 2. But there, the power is 1. Okay, times, of course, loop factors. Okay, which always involve 2 powers more for each loop level. So there, it's 3 because there are 3 fields. The operator written somewhere has 3 fields. The dipole operator.
Okay. Yeah.
So you need to count how many fields you have, okay? And that gives you the power, maybe power of the couplings.
Okay, thanks.
Okay, so now I wanted to talk about extensively about the standard model as an effective theory. Given that I have maybe 15 minutes, I will be inevitably faster, okay? And let me tell you very few things, okay? The first thing is, why do we need to consider the standard model as an effective theory, okay? We need to, because of the following observations. First of all, now we have a complete picture, no? A complete picture of the standard model, because we have measured all the parameters, including the mass of the Higgs, which was the last missing term, okay, last missing piece, as we know. And at this point, we can, now that we have all the experimental inputs, we can address whether the theory is whether the theory can be extrapolated to all arbitrarily high energies or not. Okay, whether the theory is a complete theory or is not. And now it turns out, of course, that the theory is not extendable to arbitrarily high energies, but it is extendable to pretty high energies. Okay, and that is not completely trivial in the sense that it could have been different. But it turns out, given the experimental inputs that we have, experimental values of the quantities which we have measured, that it is the case. Now, for example, consider the first observation that you can make is whether the vacuum where we live is stable or not, okay, if you assume that the theory can be extrapolated to arbitrarily high energies without having new physics, okay? Because of course, how can you test whether the vacuum is stable or not? Well, you compute the effective potential, okay, of the Higgs in the standard model, and then that's your result. So if there is new physics at a certain scale, then it will give additional contributions. Suppose that you find that our vacuum decays to another minimum, okay, which is different from our the one in which we live, too quickly. Okay, then it's clear that you need new physics. Okay, you need new physics at a scale which is sufficiently low to restore stability of your vacuum. Now, it turns out that actually we live on the verge of stability. So let me share my screen. Okay, and then you should be able to see. Okay, so this plot, this is taken from this paper here. And you see that as a function of the mass of the top and the mass of the Higgs, then there are these three regions. The red one is a one in which our vacuum is unstable, okay? And it decays faster than the lifetime of the universe. Green instead is a phase in which there is absolute stability, and the yellow one is a region in which the decay does occur, so there is an instability, but the time required to tunnel to the new vacuum is longer than the age of the universe, and we happen to be, okay, in this black spot here with a certain uncertainty, of course, because we measured top mass and the Higgs mass with a certain experimental uncertainty, and if you want to zoom, here are the 3 sigma 1, 2, and 3 sigma regions. Okay, so it's interesting that we are close to the border of stability. But anyway, for this very short discussion, the important thing is that we are not inside the region with instability. Okay, we are not in the red region. So in other words, we can live without worries. Okay, we can sleep well because there will be no vacuum decays. Okay, soon. So our vacuum is stable enough. Now, then the question is, so this is an information which tells us that we don't need any new physics, okay, to make our vacuum stable. There is, however, another question. Can we? By the way, the reason why M top is important is written here. So this is the RG equation for the quartic coupling, and there is a contribution coming from the quartic coupling itself, which gives a beta function positive, and the quartic coupling, and the correction to the beta function coming from a loop of tops is negative. So and the quartic coupling, the running of the quartic coupling is important because the potential is computed in such a way that the potential, the value of the potential at a certain value of the field, okay, is given in terms of the quartic coupling renormalized at the scale of the field at that scale, the value of the field. So in other words, you need to somehow resum the RG flow, okay? And this tells you that the top plays an important role. Now, of course, the other question is whether the theory is extrapolable, can be extrapolated up to arbitrarily high energies. And here you know that coupling runs logarithmically, but they run. Okay, and now if there are couplings which grow with the energy, then the theory it means that the theory cannot be extrapolated to arbitrarily high energy. And you see here another red region which comes, which is characterized by the fact that in any point of this region, the quartic coupling of the Higgs explodes at a scale, has a Landau pole at a scale below the mass of the Planck mass. Okay, which somehow here is taken as a reference. So in other words, if you run, okay, the coupling, since we are living well inside, okay, well far from this red region, okay, it's clear that the quartic coupling of the Higgs will explode at a scale which is much above the Planck mass. Okay, so in fact, the quartic coupling, which is this curve, is the RG evolution as a function of the renormalization scale, will actually decrease to begin with, but then at a certain point, for sufficiently high energies, it will start increasing again. In any case, there is at least another coupling, which is the Yukawa coupling, which is the red, the green dashed line, which increases already at much smaller energies. So the first Landau pole that you hit is the one of the Yukawa coupling, which, however, happens to be at energies of order 10 to the 42 GeV, so something super astronomically energies, okay? However, no matter how large are these energies, this tells you that the standard model, like QED, cannot ultimately be a complete theory. Okay, mathematically, it's not a complete theory. So it has to be considered as an effective field theory. And at this point, exactly like in the example of QED plus the dipole operator, you try to estimate. You need to write all the possible operators, estimate their coefficients, and somehow, well, do the usual machinery that you do with an effective field theory. Now, the question you might have is, did we see any effect of the high energy operators, the higher dimensional operators in the data? Well, the answer is no, except for one operator. Okay, there is the only operator which has dimension 5, because of course you start organizing the series of operators according to their dimensionality. There is only one operator which is gauge invariant, and you can write at the dimension 5 level, called the Weinberg operator. And this operator, let me stop the sharing and come back. This Weinberg operator is the one which is required to give the neutrino mass. So, of course, here by standard model, I really mean the standard model with only left-handed neutrinos, because the right-handed neutrinos are, well, first of all, they are singlets of the standard model, okay, complete singlets, so they are not really part of the standard model in its minimal formulation. And then there is no experimental data, okay, which requires them. Now you say, but look, I mean, the mass of the neutrinos are assigned that there is a right-handed chirality. Not necessarily. So you can stick to the minimal formulation of the standard model, but have one operator, the Weinberg operator at the dimension 5 level, which is written as HL, where HL, okay, is each of these two pairs, okay, of fields has SU2 left quantum numbers which are contracted with in a singlet. Okay, so each of these pair has a hypercharge 0, because this has hypercharge minus 1/2, this has hypercharge plus 1/2, and then you can contract the SU2 indices with an epsilon beta, epsilon alpha beta tensor, okay, and make an SU2 left or electroweak doublet, singlet, okay. So again, the same thing you can do here, okay. And then there will be Lorentz indices which are contracted, okay. These are the Lorentz contraction, which makes a singlet of Lorentz, okay. So this field has dimension 5. Sorry, this operator has dimension 5, and you see once you set the Higgs to its bev, it will select the upper component of both doublets, lepton doublets, and this gives you a neutrino mass. Okay, so it gives you a neutrino mass which goes like C of this operator. Let's call it C. Let's call it C. Okay, times V squared nu bar nu. Okay, so this C will go like, there are 4 fields, will go like a coupling square divided by a scale. Okay, so you see that you get exactly the right expression for a mass, okay, of the neutrinos. So unless you assume that there is light new physics, okay, in which case, of course, the effect of these new physics are not parameterizable in terms of higher dimensional operators, but will require the addition of the new light fields, no? The new physics light fields in the to supplement to be included in the Lagrangian. If you assume that there is no such new light field, then the neutrino mass must come necessarily from this operator, and hence you can claim that we have seen the effect of the effects of this operator in the data. Of course, again, we don't know the scale because we don't know the coupling. If this coupling is over the 1, then you know that the scale turns out to be of order 10 to the 14, 15 GB, which is the seesaw mechanism. So again, you see that you need to make assumptions on the UV dynamics. Okay. For all the other dimension 6 operators, instead, there is no sign of their existence. Okay. And in fact, here, as I told you, the indication is that the scale here, okay, is of order 10 to the whatever, 15, 10 to the a little bit smaller, I think, than 10 to the GV, okay, for coupling of order 1. Okay, so this means that this scale will be very, very high. Okay, and this, in a sense, justifies why we haven't seen any other effect, because this effect is a special one. The mass of the neutrinos is an operator which violates a symmetry of the standard model, which is lepton number symmetry. So this is an operator, is the first operator that you can write at the level of dimension 5, which violates this symmetry. Okay, so it's clear that other operators which don't violate this symmetry, if you set the scale to be 10 to the 15 GB, then they will give super suppressed contributions, and they are not seen in data probably because the scale is so high. On the other hand, you might infer that actually the new physics is characterized by more than one scale. So there will be one scale at which you violate lepton number, and this is necessarily very high, 10 to the 15 GB, maybe in a grand unification scheme. But then there is new physics also at a much lower scale, and this lower scale, since this new physics does not violate the lepton number, may appear, okay, in dimension 6 operators with a much larger coefficient. Okay, so that is if you want, the sense of considering the standard model as an effective field theory with a series of dimension 6 operators weighted by coefficients where the new physics scale, of course, is unknown, but can be around the electroweak scale or a bit higher. Okay, that's the range of values of the new physics scale that we can test, of course, at colliders. Now, my time is over, so I think I will I need to stop. Giuliano, do I have 5 minutes just to list?
Yes.
Okay,
Yes, no
list
problem.
just the kind of operators.
If you want to slightly expand, leave something like an open question, maybe we can also discuss during the discussion session. But in any case, you can go on for 5 minutes. There's no problem.
Yeah, give me just 5 minutes. Let me just flash here the structure of the operators, and then maybe during the discussion session, if you want, I can give more. I can answer your questions and give more details. Now, of course, here the task of classifying the dimension 6 operators is a more difficult one, because in fact it turns out that there are 59 operators. Okay, the linearly independent ones for one family. Okay, of course, in the standard model there are 3 families. Okay, and then each of these operators will have a flavor structure. But there are 59 structures, okay, 59 operators with matrices as coefficients in flavor space. Now you can see these references: Buchmüller and Weiler. This is Nuclear Physics B 268, 1986, page 621. And then there were many other papers until this other paper by Gradowski. I don't know how to pronounce it, but so this is a JHAP 1010 2010 085. Okay, so this is a long list of papers which clarified and identified all the operators, basically the minimal and complete set of bases, okay, list of operators. Now let me very quickly flash, okay, just write down the structure of these operators, because of course there are several kinds of operators. There are operators which involve, for example, only the Higgs field. Okay, for example, in a proper basis, you have this operator which is called OH. Then there is another operator which is again involving four Higgs fields and 2 derivatives. Okay, so these are fields with 2 derivatives and 4 fields. Then there is an operator with 6 fields and no derivatives. Okay, to the cube. And then you can show that the operators with 2 fields and 4 derivatives, again, as in our TOI calculation, can be removed by using the equations of motion. So it's very similar to our example, but now there are 2 operators instead of 1. And in fact, so this, you can see that it gives universal shifts to the Higgs couplings. Because you see, if you set the Higgs to 2 Higgses to their BEVs, then you get a correction to the kinetic term. Okay, and once you normalize in the canonical basis, normalize the kinetic term canonically, you get shifts in all the couplings of the Higgs. This one instead gives a correction. This gives a correction to only the mass of the Z square. Again, if you set the Higgs to its BEV, you see that you get a correction only to the mass of the Z and not to the mass of the W. So there is a symmetry which is called custodial symmetry, which relates the two, so the mass of the W and the mass of the Z. So this is a custodial symmetry, custodial breaking effect. Okay, and this operator finally can be tested, but it's the only one basically which has no constraint at the moment. It can be tested in experiments which measure the triple Higgs coupling, Okay, so it modifies the triple Higgs coupling. Then there are operators which involve 2 fermions and 3 Higgses. So basically they give modifications of the Yukawa couplings. Okay. Then there are operators which involve 2 powers of the Higgs field and 2 powers of the gauge couplings. For example, there are operators of this kind, H dagger H, F mu nu, F mu nu, or there are operators which go like d mu H, d nu H, F mu nu, or H dagger d mu H, d nu F mu nu. Okay. All these can be measured through, for example, tribal gauge coupling measurements, or, for example, Higgs decays, and so on. Okay. Then there are operators which are of the form of current times current. For example, a current of fermions, okay, times a current of Higgs. Okay, and these affect couplings to the Z. So they are very well precisely measured at lab, because you see, once you set the Higgs to its web, this current gives you a Z. Then there are 4 fermion operators, which are also current, but there are 2 currents of fermions. Okay, so these are measured, these are testable at high energy colliders, or yeah, so either lab, if these fermions are leptons, or the LHC. Okay. And then there are other operators which, for example, are of the form, let me finish here. So they are dipole operators. Okay, so you have now the same form as we wrote, but now with the Higgs field, because now gauge invariance tells us that left and right chiralities will have to be put together through a Higgs field. So these are affecting G-2, okay, and electric dipole moments, for example, and so on, very precisely measured. And what else? That there are operators which are involving only the gauge fields. For example, F mu nu cube. Okay, this is also measured through tribal gauge couplings experiments, or, for example, operators of this form. So that there is a d mu F mu nu squared. Okay. I think I've said everything, all the operators. So you see that the list is long, okay? There is a host of operators. And now one interesting question that maybe we can discuss during the discussion session is, well, okay, but before the LHC started its exploration of the weak scale, how many of these operators were already probed and constrained? There was a certain number. For example, many of these operators were constrained through electric precision tests. Okay, for example, this corresponds to the so-called T parameter. Okay, there is another kind of operator which you can identify with this, which corresponds to the S parameter. Okay, these are quantities measured in electric precision tests. But then there was a certain number of operators which were not tested before the LHC started studying the couplings of the Higgs. For example, operators of this kind were not studied before, okay? Because if you set the Higgs to its web, then you get an operator which is just the kinetic term of the gauge fields, which was already present in the Lagrangian. So any measurement of the or any measurement that you could do before exciting the Higgs boson, okay, could not resolve this versus the kinetic term of the gauge boson. Okay, so there was an ambiguity. So there is a certain list of operators. These, of course, also this one. Okay. All these operators, which are ambiguous until you excite the Higgs boson, were for the first time tested at the LHC. Finally, and this is my last comment, there is only one operator, which I already said, which is yet untested. Okay. This is the only operator which waits for an experiment, which is a measurement of the triple Higgs coupling to be tested. Okay, all the others in some a certain level of precision have been tested. Okay, of course, and I told you, and there is no experimental indication of their presence, of their effect. Okay, so in any possible experiment where we tested all these experiments, we found only bounds, okay, and never a sign of new physics. The only operator which you need is this, but it points to a scale which is very, very high, okay, at which all these other operators would give completely relevant effects. I stop here, okay. If you are interested on more details of this story, I can try and say a few words more during the discussion session and give you some references at the end. Okay.
Okay, Roberto. So thank you very much. We are a bit over time. So if there are questions, I invite you to postpone them to the discussion session where we could also expand on these last points that were only partially discussed due to the time constraints. So Roberto, thank you very much for this very nice course, and see you in the discussion session.
Thank you. Well, let me say, for those of you who will not be present during the discussion session, I want to thank all the participants, all the students for their questions and their feedback, because it was certainly stimulating, although we were at a distance, so unfortunately we could not talk in presence, but it was stimulating anywhere, and I encourage you to ask questions. I'll try to answer during the discussion session today, but also through the Slack channel. So thank you very much. Bye.
Thank you, Roberto, and see you later. I see many messages on the chat who want to.
Okay.
Many students want to thank you. But
thank you very much. Thank you, guys. Bye bye.
Okay.